In section 4.3, we're going to talk about the graphs of the tangent and cotangent functions. So we know these are two of our 6 trig functions, and they also have peculiar graphs associated with them. Let's start then with the tangent function. Since the tangent function itself is sine divided by cosine, the tangent function is the ratio between these different values around the unit circle. For the tangent function, it is going to be defined everywhere except where cosine of x is equal to 0, since that would make my denominator 0. The range of the tangent function, however, is from negative infinity to infinity. So the graph, again, looks very peculiar. If we plot what we know, in the table of values provided, we see that there are 2 places where the graph is undefined. The same way we know that at tangent of pi over 2, it's undefined. It's because the cosine would be 0. Well, undefined values are going to give us vertical asymptotes. So at both of these values, at negative pi over 2 and at pi over 2, we're going to have a vertical asymptote. Now, if we continue this pattern out, you see that every pi units after that, so from negative pi over 2 to pi over 2, it's the distance of pi. So at 3 pi over 2, I'm also going to have a vertical asymptote appear on the graph. In between those values, though, for tangent, I get that at negative pi over 4, the output is negative 1, 0 is 0, and at pi over 4 is 1. If I play connect the dots with these dots here, we see that the tangent function looks a little wonky. And if we continued this pattern, again, negative 1, 0, and 1, negative 1, 0, you would again see that the tangent function repeats itself over and over again, which is why it's part of the circular functions. Now, what does an actual period of this look like? Again, a period of this function is when the function starts to repeat itself. So if we start at 0, which is not where I started graphing, but if we look at 0, the next time this function hits 0 is here. So the period of the tangent function is not a full 2 pi units, it's actually just pi units. Here's some information about this tangent function that's really important. Its graph is discontinuous or has vertical asymptotes at values of x of the form pi over 2 plus pi times n, where n is an integer. Basically, these vertical asymptotes for a regular graph are going to appear at plus or minus pi over 2. So when the x value is equal to plus or minus pi over 2, we'll have a vertical asymptote. It has x-intercepts at repeating values of 0 plus pi times n. So every pi distance away from 0, there is going to be an x-intercept. Like we said, the period of the tangent function is just pi instead of 2 pi, which also means, important for us when we're writing our transformations, the b value here is not going to be 2 pi divided by the period, it's just going to be pi divided by the period of the tangent function. So that is a change from sine and cosine, since the regular period of tangent is not 2 pi, it is just pi. Since there are no minimum or maximum values, seeing that the arrows go down and up infinitely, the graph has no amplitude. The graph is symmetric with respect to the origin, so I could rotate it around the origin, so the graph is an odd function. For all x in the domain, tangent of negative x is again equal to negative tangent of x. These even odd identities will come back to us in the next chapter, but it is important to see that here attached to the graph. If we talk about the cotangent function is the ratio of cosine to sine, which means this time there's going to be undefined values where sine is equal to 0. However, its range is still from negative infinity to infinity. It just has restrictions on its domain. So again, if we notice in the graph of values where we have undefined moments, those are where my vertical asymptotes are going to be. That's where sine is equal to 0. Sine is equal to 0 at 0 and at pi. And if we keep this pattern going, it would be again at 2 pi. And if we look at the values in between, at pi over 4, I'm at a value of 1. Pi over 2 is 0. 3 pi over 4 is negative 1. And we can repeat those values here. When we play connect the dots here, connecting these values together and abiding by the fact that you can only come close to, you cannot cross a vertical asymptote, the cotangent function looks a little bit something like this. So it's decreasing the entire time instead of increasing. This graph is discontinuous at values of x that are of the form, so the vertical asymptotes appear at 0 and every pi value after that. So for your vertical asymptotes are going to appear at 0 and at pi. That's the important thing for us here. Plus or minus pi in every value after that. The x-intercepts, if you look at your graph, start at pi over 2 and then appear every pi after that, where n is an integer. The period of the cotangent function is also pi, so like with tangent, the b value is going to be pi divided by the period, not 2 pi divided by the period. Again, no maximum minimum value, so it has no amplitude. This one is also symmetric to the origin, so I could rotate this around the origin and it would land right on top of itself, and that means that it is an odd function. For the even odd identities, cotangent of negative x is equal to cotangent of x. So if we think about some techniques for graphing, we're going to leave the tables that we did last time apart, because the important thing with tangent and cotangent is identifying where your vertical asymptotes and where your x-intercepts would be. That means that the things we would do for this graph, for graphing y equals tangent of 2x, we would need to find the places for all the vertical asymptotes. But I know that vertical asymptotes for this graph are going to appear when the 2x is equal to plus or minus pi over 2. When the argument of tangent is equal to plus or minus pi over 2. So divide by 2 on both sides. Pi over 2 divided by 2 is pi over 4. So I'm going to have vertical asymptotes at negative pi over 4 and at pi over 4. The other things I learned from this is that the a value, the vertical dilation, is 1. There's no stretch or shrink here. The b value is going to be 2. Now this is important because it means for me that the period of this graph is equal to pi over 2. Pi divided by b. So I should finish an entire wave, an entire curve for this tangent function in pi over 2 distance. Just kind of going back to what we learned with the transformations, there is no shift to this midline nor to the phase of it at all. So if we plot this, here's what I want you to be able to identify. We again need to know where my vertical asymptotes are. And we said that those would appear at negative pi over 4 and at pi over 4. So let's draw in some vertical asymptotes. I'm going to continue to use orange as my color for vertical asymptotes here. And voila, here's my vertical asymptotes. Cool. I also know that this is a tangent function, so it should be increasing on the intervals in between that. Right in the middle, we should have our x-intercept in the middle of those vertical asymptotes. And the values in between that should be a low point and a high point, so that then I can come in and play connect the dots to create one period for this tangent function. Now, obviously, this would repeat again, so if I wanted to graph more, I'd have some sort of graph that does this and on both sides of these vertical asymptotes. So again, I need you to identify where the vertical asymptotes would appear so that you know the entire function takes place in between them. And just make sure you know of any a dilations, some vertical dilations with the a value to these points right here that are not maxes and mins, but they act as low points and high points for the curve as we get closer to the vertical asymptotes. Let's try another one. We're going to graph y equal to negative 3 times the tangent of 1/2 x. Now, like I said, we need to identify where our vertical asymptotes would be. For this graph, since it is tangent, we know the vertical asymptotes are going to appear when the argument 1/2 x is equal to plus or minus pi over 2. Multiplying by 2 on both sides, that means I'm going to have vertical asymptotes at pi. If we look at our values here, the a value is negative 3, so that means that I'm going to not only vertically dilate this, I'm also going to reflect. And me being me, I need to write down that this is reflected or else I will forget. So no longer will tangent be increasing, the points should be decreasing. My b value is 1/2, which means that the period is pi divided by 1/2, and pi divided by 1/2, is 2 pi. For this one, there's no phase shift and there's no vertical translation. So this is pretty simple. So we graph these vertical asymptotes. I said that they would appear at negative pi and at pi. So let's draw those in. We have our vertical asymptotes. And again, I know that these values, since it's stretched by 3, should have those, they're not minimum and maximums, but I like to think of them as minimum and maximums. The other coordinate points I'm plotting at least, at 3 and at -3. But I also know this has been reflected. So instead of increasing for this tangent function, I'm going to decrease. So at the intermediate points here, I should be starting up and then going down so that it's decreasing. Playing connect the dots, here's what your tangent function will look like if it has been reflected and stretched by 3 with a period of 2 pi. In our next example, we're going to be graphing a 1/2 cotangent of 2x. Ooh, cotangent, so this is different. For cotangents, our vertical asymptotes are going to appear where 2x is equal to 0 and where 2x is equal to pi. Plus or minus pi technically, but we're just going to do one of them. We're going to do the positive pi. That means that we'll have a vertical asymptote at 0, and we'll have a vertical asymptote at pi over 2, and another one at negative pi over 2. If we look at the other values we have, we know that the a value is 1/2, so my other points, the points in the intermediate, are going to not go up to 1 and -1, but to 1/2 and -1/2. My b value is 2, which means that the period of cotangent would be pi divided by 2, so sorry. And because there is no phase shift and no midline change, we aren't going to shift this in any way. That's a weird looking D. Let me try that again. Okay, plot what we know, because we only need one period of this graph. We know that at 0, there is going to be a vertical asymptote. We also know that at the value of pi, there is also going to be a vertical asymptote. Cotangent needs to appear in between that. So in the middle, which is pi over 2, I would have my middle point, and then the intermediate points will create the other parts of this curve. Now again, this is cotangent. Cotangent should be decreasing. So I'm going to put a point halfway between 0 and 1, and halfway between 0 and -1 for the other points that I need to plot. Playing connect the dots, we have cotangent. We're just going to keep plotting some of these functions here. Y equal 2 plus tangent of x. Again, I notice that this is tangent. That means that the vertical asymptotes are going to appear at where the argument is equal to plus or minus pi over 2. Well, I don't have to solve anything for this one, so I automatically know that at negative pi over 2 and at positive pi over 2, I'm going to have vertical asymptotes. So I could just go ahead and draw those in because I know that that is going to happen. It's a great way to eliminate answer choices if you're given pictures of graph, is looking where those vertical asymptotes are. For the rest of this function, I see that there is no vertical dilation because there's a 1 in front of tangent. There is no change to the period. That means that the period is just going to be pi like normal. And I don't see any phase shift, which is D, so there's not any phase shift. But I see, see what I did there, that this C value is 2, which means I have a midline that has been shifted up to the value of 2. Now this is where drawing the actual dashed line for the midline might get confusing. I still think it's really helpful to see that midline. This is not a horizontal asymptote. So we usually draw asymptotes with the dashed lines, but I need to see the midline of this function, so I put things in the right spots. So I like drawing the midlines. If that confuses you, don't draw your midline. Now this is tangent. Tangent is increasing. So in between these vertical asymptotes, I should have a midline right in the middle, and then other values on the other side of the midline that go up 1 and down 1 to create the other values that make this tangent graph increase. So playing connect the dots, it looks something like that. Obviously, again, I don't want you to just think that this happens once. For tangent and for cotangent, these curves occur indefinitely from -infinity to infinity across the entire graph. We're just only graphing one period or one little curve of it. Last example on this page, we're going to be graphing a more complicated cotangent function. Not a big deal. Let's do what we've always done, which means we're going to look for the vertical asymptotes first. This is cotangent, so vertical asymptotes are going to appear where the argument is equal to 0 and where the argument is equal to pi. So if I add pi over 4 to both sides, that means I'm going to have a vertical asymptote at pi over 4, and I'm going to have a vertical asymptote at 5 pi over 4. I could go ahead and draw those in. So here's pi over 4, then 2, 3, 4, 5 pi over 4. Both of those values should be where there are vertical asymptotes for this graph. I already know that, so that's going to be the period that I draw in between those two vertical asymptotes. Let's see what else happens here. The a value, the number in front of cotangent, is -1, so that for me, again, I need to note to myself that this has been reflected. So cotangent was decreasing, and it's been reflected, so now it should be increasing. The b value is 1, which means that the period is pi. The d value, the phase shift, is pi over 4, which means we should have a phase shift or scooting away from the y-axis by pi over 4. We can already see that we're going to do that since we drew one of our vertical asymptotes to start at pi over 4. Last but not least, the midline is at -2. So again, if this confuses you to have a midline showing, maybe don't draw the dashed line for the midline itself. I find it helpful for me, but if it's confusing to you, don't worry about it. Now this is cotangent. Cotangent is normally decreasing. But since I have reflected this cotangent, when I get my next value, I should just be going up to the right and down to the left. So this is -3, this is -1. If I connect the dots here, here's what this cotangent for one period would look like. In example 6, we're working backwards. So I've given you a picture, one period, of either a tangent or a cotangent function, and your job is to determine an equation for it. We need to identify a, b, c, and d, and what type of function it is. Well, I see here in this function that we have vertical asymptotes at -pi over 2 and at pi over 2. That's an indicator to me, since the vertical asymptotes are at plus or minus pi over 2. That means to me that this is a tangent function. So I know what I'm going to be writing. I now just need to figure out what a, what b, what d, and what c are going to be equal to. Well, I know that this is tangent, okay? But I know that tangent should be increasing. Since this is decreasing, I know I've been reflected, and I've also been stretched out to 2. Normally, these other intermediate points are at positive and -1. Well, I'm at positive and -2. So my a value is -2. Again, reflected because tangent is typically increasing. To find the b value, you're going to actually see how long it takes to go from one vertical asymptote to the other. That is a distance of pi. So if I figure out that p is pi divided by pi, b is pi divided by pi, b value is just 1. Since I have a midline happening on the origin, 0, 0, there is no phase shift, so that would be the number 0. And I haven't moved up or down, so my c value is also 0. There's no change to the midline. So this function would be y equal to -2 times the tangent of x. None of the other numbers besides the a value have been affected, so it's just a simple vertical dilation and reflection of the normal tangent function. For part B, again, if we'd followed the same thought process, we're going to identify where the vertical asymptotes appear. There's not one dashed here because you can't put dash line over a solid line, but if you notice, I have vertical asymptotes at 0 and at pi. That means that this is cotangent. Okay, now we just need to know the a, b, c, and d values so that we can put the numbers in the right spots. The a value would have to do with any sort of dilation or reflection vertically. But if I notice, this is a decreasing function. Cotangent should be decreasing. We're fine. We don't have to reflect it. And this has a distance of 1, which means there is really no vertical dilation. That number is 1. If we check out the amount of time it takes to go from one vertical asymptote to the other, it takes pi over 2 time to go to the vertical asymptote. So if I find the b value, it would be pi divided by pi over 2. The pi's cancel. This just becomes 2. Since I have a vertical asymptote at 0, there is no phase shift for this graph. We're not moving it side to side. But there is a change to the midline. If you notice where I highlighted blue here, where the middle point is, it's at -1, which means this c value is -1. Including all of those changes, so the numbers that we need to include, I would write that this equation is y equal to -1 plus the cotangent of 2x. Or if you like putting the vertical translation at the end, you could also write this as cotangent of 2x, all of that -1. Your book prefers the first version, but they're mathematically equivalent.